Section 415 is called Controlling the Voltage of a Shunt Generator. Maybe a better title for 415 would be Controlling the Voltage Output of a Shunt Generator. And so, building on what we've gotten in the earlier sections, we want to incorporate something into this parallel or shunt generator connection, and so we can vary it such that we can get a precise voltage output from this shunt generator. So let's look how we might be able to do that. So here was this self-excited shunt generator, and we said that it was shunt generator based on the field being in parallel with the armature here, right? So this is the parallel connection of the shunt field supplying the flux to generate the voltage output. Now, what we have here, we don't have any way to control this this output voltage, because whatever the resistance of this coil is, it is the the total resistance of that parallel circuit. So what if we put something called a rheostat? And a rheostat is a variable resistor. So I'm going to incorporate this rheostat into this circuit that we had from figure 419, and I'm going to figure out a way to control this so that I can get a precise output voltage in that case. All right, so we do that, and the way this is done, it's shown in figure 420, and here's our armature voltage here. Here's our output. This is where the brushes were, and this is where we would connect the load eventually. Here's our excitation current, I sub x. Here's our field. It's in parallel, right? It's in parallel with the armature. But what's different now is we've got this field rheostat. And so what we're trying to show here is that we can move this connection to this field rheostat up to point N, and when we do that, we have maximum resistance at the N position, or we can move it down to the M position and have minimum resistance at that point. Okay, so that's sort of the idea. That's the thing that we want to think about. And he defines this term here on page 81, and it is R sub T, which is the total resistance between this point of connection and this point B here. All right, and again, it's variable, right? It can be increased or decreased based on where we move our connection to this field rheostat. All right, and so this total resistance that we have, we're calling it R sub T. All right, so going along with that line of thinking, he says we can determine the no load, and something I haven't talked about too much yet is that everything we've been discussing here in the last few sections is in a no load situation. There is no load connected to this generator. We'll see some different things happen when we do connect the load, but right now we're trying to understand it under this no load condition. And he says we can determine the no load value of the saturation curve of the generator and the total resistance of the shunt field. And what we could do is we could draw a straight line corresponding to the slope of whatever this total resistance is. Okay, we could get up a point on here and we could draw a straight line, and this straight line resistance is equal to the voltage divided by the current, right? And this value for a resistor, if you'll think back to ELC 131, it was a straight line, right? You know, if I had current here and voltage here, and I had a particular resistance, the greater the resistance, the greater the slope. Say this is resistance equal to 100, and then if I had another less resistor, it would have less slope. Maybe this is a resistance of 50 ohms. But regardless, that resistance never changed, right? It's consistent across there. So what he's saying here in this situation that we have with this setup, where we're looking at the total resistance between the point of connection and the point B, we could draw these, we could superimpose these straight line uh, correspondence to the saturation curve. And what we end up with is something that looks like this, which is really kind of neat and explains a lot about what's going on with our machine. So what he's saying in our particular case is the shunt field has a resistance of 50 ohms, and we plot that straight line of 50 ohms, which is, you know, voltage divided by current, Ohm's law. Then the line corresponding to RT must pass through a coordinate point of 50 volts divided by 1 amp, which would give us 50 ohms. So where would that be on our curve? Well, here's 1 amp, and I'll follow that up here. Here's 50 volts, and that's where this curve would hit. All right, just, you know, if I went to 100 volts, okay, and 2 amps, 2 amps, follow it up to the curve, hits at 100 volts, right? And that's, you know, because this resistance is 50 ohms, you know, all these different combinations, and, you know, I mean, not to oversimplify that, but, you know, that's where this straight line comes from. Now, if we have these different resistances, we can superimpose them on the saturation curve, which we talked about earlier, right? It looks like this. This is characteristic of the particular generator that we're looking at. And if we see, like here is the minimum resistance, we could see where these two curves intersect. And we could do this totally mathematically as well. We see that the maximum voltage output for this generator would hit here for 150 volts. Okay, all right, makes sense. Then I could pick another point. Say I'm another point here, and I'm altering the connection to the field rheostat, and say that I'm looking at a total resistance of 120 ohms. Again, I'm going to plot that same curve, and just to give you a real simple example of that, if this is 120 ohms, then what that should mean is at 1 amp, based on Ohm's law, 120 volts divided by 1 amp, right? 120 ohms. Let's see if that works, right? If I go up the curve, you know, 1 amp, 120 volts. If I was at, say, let's see, I can't get I can't do that for 2 amps, but I could do it for the other points on here. And I could, you know, that's how I can plot this straight line for the resistance. And that's where this curve comes from. And what this shows us with this particular intersection is this shows us where this resistance would intersect on the saturation curve. So he says by changing the setting on the rheostat, the total resistance of the field increases, causing E sub O to decrease because the excitation current is decreasing, the voltage is decreasing, and we see the resistive line cuts the saturation curve at 120 volts. If we continue to raise RT, if we continue to increase it, at some point, we're going to hit this place right here, okay? And what that point on the curve actually is a critical value where the slope of the resistance line is actually equal to the saturation curve, right? They're right there on top of each other. We can't even discern a difference between the two. And what he tells us there is that in this situation, when this resistance is attained, the induced voltage suddenly drops to zero and will remain so for any R sub t greater than this, okay? Excuse me. And so where we couldn't operate this generator would be values where this total resistance here was greater than 200 ohms because it is beyond the saturation curve. It's not even going to hit the curve, so we're not going to get a voltage output. So anyway, I just think that's really interesting, you know, to be able to quantify that, to look at the curves. One thing that I like about, you know, what we do in this field as opposed to, say, doing this purely mathematically, you know, we're looking at this graphically, you know, and we can understand it better that way. Again, we could look at the intersection. We could do this mathematically in the intersection of two curves. But what we're doing is we're actually seeing these points on the curve, and I think that helps us to understand that when we're trying to understand how these electrical machines actually work.